In this video, we're going to go through question 13 from the NESA Sample HSC Mathematics Extension 2 exam. Question A. It is given that A and B are positive real numbers. Consider the statement for all A and for all B, A to the power log B equals B to the power log A. Either prove the statement is true or provide a counterexample. Alright, so this question, we don't know whether our statement is true or not. We either want to prove it if it is true or provide a counterexample. So what I would be doing is I would be plugging in values for A and B that satisfy the condition that A and B are positive real numbers. Okay, so they're real numbers and we know that they're positive, so sometimes we write that by this little subscript greater than 0 to indicate that they're bigger than 0, that they're positive. So I would start subbing in a few values and seeing if this does check out. And I think that when you do that, you will find that this does check out. So then I'd start thinking about, well, how can I prove it? I wouldn't spend too much time subbing in. Once I've subbed in a couple of values and I've got an idea or a bit of intuition into what I think, whether it's true or not, then I would start to either prove or disprove. Okay, obviously you would be disproving through use of a counterexample. So we want to prove this, so that means we need a proper proof. And what I would be doing is I would be playing around with this on the side of the paper, maybe in pencil, or maybe if you have scrap paper, although I don't think you really get scrap paper in a HSC exam. But I'd start playing around with this. So I'm going to actually start off with what I want to get. Now this is not a good idea to do when you're writing your final answer. However, on the side of the paper, when you're doing some working out, it's actually not a bad idea. As long as you make sure that you don't start off with what you're trying to prove when you write down your final answer, because that's known as a circular argument and it's not logically correct. So I'd start off with this, and I can see that I've got some stuff in the powers, and having things in a power is not really ideal. So I'd like to somehow bring these down out of the power. And the way I could do that is by taking the log of both sides. So this would only be true. Now you can see I've put a double implication sign. So this statement is true if and only if the log of both sides is true. So this is true if and only if this is true. And of course we took the logs so that these powers can come down to the front. Okay, because we know that that's part of our one of our log laws. And this is only true if and only if this is true. Now we're applying our log laws. That should be an A here, I believe. So let me just fix that up. A log A times log B. And we can see that this statement here, well, that certainly is true because the order in which we multiply two things doesn't really matter. These are both real numbers. So if I do log B times log A or log A times log B, it's not going to make a difference. So I know that this is certainly a true statement. And I think that this is pretty basic enough to start off with our proof. Okay, so what we're going to do when we go back to do our proof, we can indicate that it's true by saying proof, because now we're telling the reader that I am about to prove this statement. We know that log of B times log of A is equal to the log of A times the log of B. And so what I'm going to do is I'm actually going to reverse engineer this working out here. I'm going to go back in the opposite direction. So I'm starting with this, which is what I wrote down, and now I'm going to write down this as my next step. And then after that, this would be my next step, and I'd arrive at my final result. So really what I've done, I've actually done my proof on the side here, but I've just done it backwards. And then when I want to do it properly, I just write it back to front. So this would imply, by our log laws, that log of A to the power log B is equal to log of B to the power log A, ln A. And you might want to indicate here by log laws. So I would say by logarithm laws. And then this indicates, or this implies, that A to the log B, and maybe even at this step, instead of going straight to it, I would make it extremely explicit and write e to the power log of a log b equals e to the power log of b to the log a. And now, because we've got exponential to the power of a log, they cancel and we get a to the log b equals b to the log a. And that's the end of our proof. We can indicate that by like a box, or maybe you write QED or something like that. Okay, and that is the end of our proof. Question B. Consider the polynomial p sub n of x equals x plus 1 to the power of 2n plus 1 plus x to the n plus 2. Let omega be a cube root of unity where omega is not equal to 1. By considering p sub n of omega and p sub n of omega squared, prove that x squared plus x plus 1 is a factor of p sub n of x. Okay, so we want to prove that x squared plus x plus 1 is a factor of this polynomial. And they've given us a hint. They said to consider p sub n of omega and p sub n of omega squared. Okay, now let's think about what omega is, because they've given us some information about what that is. They've told us that it's a cube root of unity, and they've been very specific and said that it's not equal to 1. Now, hopefully, you're quite familiar with cube roots of unity, because they are really important. We know that there are 3 cube roots of unity. One of them is going to be 1, and that's something that you would know from even year 10 and below, taking cube roots. But then the other 2 are going to be complex solutions. Okay, so let's work firstly with the omega, with the cube root of unity, and see what we can come up with. Okay, so since omega is a cube root of unity, we have the following. Omega cubed is equal to 1. Okay. Let's move the 1 over to the other side, to the left-hand side. We get omega cubed minus 1 equals 0. And hopefully you're familiar enough with what you need to do at this stage. You really need to factorize this left-hand side here, this omega cubed minus 1. And this is a difference of 2 cubes, but we know how to do, or hopefully we know how to do a difference of any power. This is going to turn out to be omega minus 1 times 1 plus omega squared equal to 0. If you're unsure about this, this is something that you really will need to be familiar with going into a HSC exam or any exam where you're looking at complex numbers and roots of unity, because this often pops up. It's quite an important concept, especially this factorization. So what does that tell us? It tells us that omega minus 1 equals 0, or 1 plus omega squared is equal to 0. But of course, the question told us that omega is not equal to 1. Okay, sometimes this fact is disguised by saying omega is a non-real root. Okay, so they won't say that specifically omega isn't equal to 1. They might say that omega is a non-real root. And if it's a non-real root, well then it can't be equal to 1, because 1 is a real number. Either way, we say since omega is not equal to 1, or since omega is not real, if that was what they told you in the question, that means that 1 plus omega squared is equal to 0, and not this case. Okay, obviously not that case, because we've said omega is not equal to 1. So good, we have this condition on omega here. Let's do a little bit more, because we know in the question they told us to consider p sub n of omega and p sub n of omega squared. Okay, so I want to see if I can somehow get an expression for omega and for omega squared. And I can. So this tells us that omega is equal to minus 1 minus omega squared. And omega squared is minus 1 minus omega. So here are 2 expressions for omega and omega squared. Okay, so it's good to have these sort of in your back pocket, because when we want to look at p of omega and p of omega squared, we've got these to work with if need be. So let's start off with p sub n of omega. Well, what was p P of x. It's written up here, so all I need to do is substitute in omega. Okay, so we have omega plus 1 to the power 2n plus 1 plus x, not x, because I'm subbing in omega, so this should be omega to the n plus 2, which is alright. But now I want to somehow show, well, what should I be aiming for? Remember that our final task, and maybe I should have written this up here and I'll write it in blue, we're required to prove that 1 plus x squared is a factor of p sub n of x. So I want to prove that this is a factor, and I know that the roots of this thing, when I solve it equal to 0, are going to be my complex roots of unity, so omega and omega squared, right? And that's actually what we've kind of got here. We know that if I substitute in omega to that, it's going to satisfy it. So really what my aim is, I can translate this required to prove. What I really want to show is that p sub n of omega equals 0, and p sub n of omega squared is equal to 0. Because that would mean that x minus omega and x minus omega squared are factors of p sub n of x. And then this times this is actually going to give me exactly what I want, because I know that omega and omega squared are the roots of this. So this here is really my aim at the moment. I'm trying to show that this is going to be equal to 0, and this is going to be equal to 0, and when I substitute in omega squared, that's going to be equal to 0. So let's aim for that. And it's always really important when you're solving these problems is to get an understanding of what you're going for and then to really go for it. Okay, so somehow I want to show that this is equal to 0. But at the moment, I really don't have any idea how to go about it. I don't want to have to expand this out, and I don't think that would be very helpful either. Although what we did do is we wrote some expressions up here, and somehow I think that these are going to be helpful. And what I'm going to do with this one is I'm actually going to rewrite it in this way. I'm going to write it as minus omega squared equals 1 plus omega. And the reason I've done that is because I can see that I've got a 1 plus omega here, so I want to match that up with this. So now I have something to substitute in for. So instead of omega plus 1, I'm going to write minus omega squared to the 2n plus 1. Okay, so now we need to try to simplify this. Now 2n plus 1 is guaranteed to be an odd number if n is an integer, and n is an integer. So this is guaranteed to be an odd number, which means that I have negative 1 to an odd power, which means I'm going to get out negative 1. So this is going to end up being negative, and then it's going to be negative omega to the power of 2 times 2n plus 1, which would be 4n plus 2. Okay, so just convince yourself of that. Plus omega to the n plus 2. Let's factor out something here. Let's try to factor out an omega to the n plus 2 from both terms. So I'm taking out an omega to the n plus 2, which means from each of these powers, I want to subtract n plus 2. So I have minus omega. If I subtract n plus 2 from 4n plus 2, I'd be left with 3 to the power n. 3n as the power. And from my second term, well, I'm only going to be left with a 1. Now, let's have a look at what this is. On the side here, omega to the 3n is omega cubed all to the power n. And what is omega cubed? Omega cubed is equal to 1, because that's what the definition of a cube root of unity is. It means that when I cube it, I get 1. All right, and we actually wrote that up here. So this bit here is equal to 1. And so minus omega to the 3n is going to be minus 1. So I have omega, let's continue this in black for consistency, omega to the n plus 2 times minus 1 plus 1. And of course, minus 1 plus 1 is 0, and anything times 0 is 0. So I've got to my first sort of sub-aim. I've shown that p of omega is equal to 0. Now I want to try to do the same thing for p of omega squared. But maybe we should also indicate here that by the factor theorem, this means that x minus omega is a factor of p sub n of x. Okay, and you might like to write by factor theorem, just to justify your reasoning. Let's now have a look at this one, p of omega squared. Substituting that into our expression, we would get omega squared plus 1 to the 2n plus 1 plus omega squared to the n plus 2. And just like we did up here, where we got an expression for 1 plus omega, I think it's a good idea if we get an expression for 1 plus omega squared from here. So this is going to be minus omega equals 1 plus omega squared. So let's substitute this in now into our polynomial. So this was going to turn out to be minus omega to the 2n plus 1 plus omega to the 2 times n plus 2, so 2n plus 4. Okay, once again, we have minus 1 to an odd power, which means it's definitely going to be negative. So we have minus omega to the 2n plus 1 plus omega to the 2n plus 4. All right, let's factor out an omega to the 2n plus 1. From the first term, I'm left with minus 1, and from the second term, I'm left with omega cubed. Of course, we know that omega cubed is 1, because that's the definition of a cube root of unity. So this is negative 1 plus 1, which is, of course, 0. And so we get that this is equal to 0, which, just like before, implies that x minus omega squared is a factor of Pn of x, also by the factor theorem. Now, maybe we should call this statement up here statement number 1, statement number 2. And so if each of them are factors of Pn by 1 and 2, we've got that x minus omega times x minus omega squared is a factor of Pn of x. So x minus omega times x minus omega squared. Well, this is going to be x squared minus omega plus omega squared times x plus omega cubed. And I'll let you check that that's the case. But really what we just did, we expanded and then simplified like terms. This is x squared minus something times x plus omega cubed. What's omega cubed? Well, we've already said it a few times. That's equal to 1. What's the thing that goes in here? What's omega plus omega squared? Well, if we go all the way back up to the top, omega plus omega squared plus 1 is equal to 0. So if I moved the 1 over to the left-hand side, sorry, to the right-hand side, I'd get omega plus omega squared equals minus 1. So this bit in here is a minus 1. And so we have x squared plus x plus 1 is a factor of Pn of x. Really, I should put some implication signs all the way along here. Okay, but we've proven what we want to prove, so we can say QED. And that's the end of part B. Question C. A particle of mass 0.5 kilograms is dropped from the top of a tower of height h meters above the ground. The particle experiences a force due to air resistance of magnitude v squared over 1000 newtons, where v is the speed of the particle in meters per second. Let the displacement x meters at time t seconds be measured in a downwards direction. Part I. Show that the equation of motion of the particle is x double dot equals g minus v squared on 500, where g is the acceleration due to gravity. Okay, so this is the expression here that we're trying to prove. Let's get a bit of a diagram going to see exactly what's going on. So this is going to be the top of our tower, and our ball or our particle, which we're going to represent as this circle here, This is our particle, and this is going to be dropped, and it's going to eventually reach the ground. So let's draw in our ground. Usually when I draw in a ground, I put this little dashed thing underneath it just so I know that this is the ground. And we know that the height of the ball at the moment is h meters, because the height of the tower is h meters. So this distance from here to here is h. Now it says that there was an air resistance equal to v squared over 1000. The magnitude of the air resistance was v squared over 1000. Now if our particle is moving downwards in this direction, we have the force of gravity, obviously, which is mg. And since it's an air resistance, the resistance means it's going to be in the opposite direction to the motion. So that means the air resistance is going this way. I'm going to label this as F air. This one I'll probably label as Fg for gravity. The air resistance is going in the opposite direction, and the magnitude was equal to v squared over 1000. And we're also defining, I believe the question defined that the direction of motion was going to be downward. So this is the positive direction of motion. Positive direction of motion. Okay, so we've got everything sort of put in on our diagram. Now we just have to make sense of it. So Newton's second law says that the sum of forces, let's get rid of this, sum of forces equals mass times acceleration. All right, now what are our forces? Well, we've only got two forces. We've got the force of gravity and the force of the air resistance. So the force of gravity is in the same direction as the direction of positive motion, what we've defined here to be the direction of positive motion. So that means this has a positive sign. So this is going to be mg. But our air resistance is in the opposite direction, which means that it's going to have a negative sign. So this would be minus v squared over 1000 equal to ma. Now what is the mass? Well, it tells us in the question that the mass is 0.5 kilograms, or it's just a half. So we can substitute that in as a half. And then to get to the result that we want, I think we just need to multiply through by 2 and we'll get there. So if we multiply everything by 2, we'll get g minus v squared over 500 equals the acceleration. But of course we can write acceleration as x double dot. And then this is exactly what we were required to prove. So we can write QED here and we're done. Part 2. Show by integrating using partial fractions that v equals 70 times e to the 0.28t minus 1 over e to the 0.28t plus 1. Okay, so it's telling us to integrate using partial fractions. Now this is what we're trying to get to, and this is the result that we got in the first bit. And the question has also said to use that g is equal to 9.8 meters per second per second. Okay, so somehow we want to try to involve v's and t's in this expression so that we can integrate it and then eventually end up at this. So since we want an expression here which involves v's and t's, we want to try to write our x double dot in a way that involves v's and t's. We've already got v's here, which is good, but we want x double dot to involve v's and t's, and the easiest way to do that is to just write it in its simplest form, dv on dt, because acceleration is the first derivative of velocity with respect to time. So this is going to be dv on dt equals g, which we now know is 9.8 meters per second. So this is 9.8 minus v squared over 500. If I create a common denominator on the right-hand side here, so I get everything over 500, I believe 9.8 times 500 is 4,900 minus v squared all over 500. Okay, so this is dv on dt. Now, what I'm going to do is I'm going to move my numerator here down to this denominator, and I'm going to move this denominator up as the numerator here. So I get dv all over 4,900 minus v squared equals dt over 500. And from here, I'm going to integrate both sides. Now, the question did tell us that we need to use integration by parts, but even if it didn't, we know that we would have to use integration by parts in this integral here. So let's try to factorize it first, and I can see that this is a difference of two squares because I know that 4,900 minus v squared is really 70 squared minus v squared, and then that factorizes into 70 minus v, 70 plus v. So I'm going to factorize my denominator here. I get dv over 70 minus v, 70 plus v, is equal to, now this integral, we could probably just go ahead and evaluate it now. That's going to be t over 500. That one's quite simple. But now we need to do a partial fraction decomposition on our integrand here so that we're able to actually do our integral. So I'm going to do that in a different color. I might do it in green. I want it to eventually look like 70 or a over 70 minus v plus b over 70 plus v. I want that to be equal to 1 over, I suppose it's 4,900 minus v squared. And then if I just equate numerators, this would be a times 70 plus v plus b into 70 minus v should be identical to 1. All right, so I'm going to start by letting v equal positive 70. That will eliminate this term, that'll become 0. So this term becomes 0, and I get a times 140 equal to 1, which means that a is 1 over 140. And if I let v equal minus 70, now this term becomes 0, and so this disappears, and we get b into 70 minus 70. That'll be 140 equal to 1, and so b is also equal to 1 over 140. So now I can substitute this information, or these two constants, into this, and then I can substitute that back into my integrand. So let's go ahead and do that. The integral is going to be a, which is 1 over 140, over 70 minus v, plus b, which is 1 over 140 as well, over 70 plus v. I'm integrating all of that with respect to v, and that's equal to t over 500. Okay, now these are fairly easy to integrate because these are just logarithms. This is a log and this is a log. So this would be 1 over 140 times minus 1 times log of 70 minus v. Now make sure that you have this minus 1 in here, because what we would have to do, we would really be multiplying this by minus 1 and then a minus 1 out here, just so that we have the derivative of this on top, which is a minus 1. Okay, and then plus, let's do it in black, plus 1 over 140 log of 70 plus v. Now, since we've evaluated all of our integrals, now we will need to add in a constant. This is our constant of integration plus c. Okay, we can actually combine these two expressions together using our log laws. It's going to be 1 over 140 log of 70 plus v over 70 minus v. Keep forgetting that plus c, plus our constant equals t over 500. Now we need to use our initial conditions, or some conditions given to us in the question, to work out this constant of integration c. And if we go back to our diagram of our particle, at this point up here, the time is equal to 0, and the velocity is also equal to 0, because it hasn't moved yet. Once we drop it, then it starts gaining some velocity. But at the moment that we drop it, at the very instant that it's dropped, it doesn't have any velocity. It's dropped without velocity, or with a speed of 0. So that means that we can use that condition. When t equals 0, the velocity is equal to 0. So we substitute that in, and what do we get? 1 over 140 log of 70 plus 0 over 70 minus 0. So 70 on 70 plus c equals 0 over 500, which is just 0. Now this term in here, 70 on 70 is 1, and log of 1 is equal to 0. So in fact, this entire term is equal to 0. So I've got 0 plus c equals 0, which means c is equal to 0. And it often turns out to be the case that questions are designed for c to be equal to 0, but you cannot assume that. You have to show that the constant is equal to 0. And it might turn out that it's not, but it just happens for convenience that a lot of the time c is equal to 0. Anyway, so this means that we have 1 over 140 log of 70 plus v over 70 minus v equals t on 500. Now, our original question is asking us to show that, where is it? It wants v in terms of t. So I want to try to make v the subject down here in this rather nasty looking expression here. I'm going to fix that 7 up. First step is probably to multiply by 140. When we do that, we get log of 70 plus v over 70 minus v. We'll get 140 on 500, and if you put that into your calculator, you'll get 0.28 times t, and that's a good sign because that's popping up in the expression that we want to prove. What else is popping up in that expression? Well, we see a lot of exponentials, and we don't see any logs. So we want to get rid of this log. The best way to do that is to take the exponential of both sides. So we'd get 70 plus v over 70 minus v equals e to the 0.28 t. All right, now I'm going to multiply both sides by this denominator here. So 70 plus v equals e to the 0.28 t times 70 minus v. Expanding that out, we get 70 times e to the 0.28 t minus v times e to the 0.28 t. Now I'm going to bring everything involving a v to the left-hand side and everything else to the right-hand side. So I've got a v already on the left-hand side, and I'm going to bring this over to the left-hand side. We get plus v e to the 0.28 t is equal to 70 e to the 0.28 t, and I'm going to bring this 70 over to this side, and that becomes minus 70. On the left-hand side, I factor out a v, and I get v times 1 plus e to the 0.28 t. On the right-hand side, I'll factor out a 70, and I'll get e to the 0.28 t minus 1 in my brackets. And then just dividing through by this factor here, and I'll get my final answer. 70 e to the 0.28 t minus 1 all over 1 plus e to the 0.28 t, and then we can write QED because we've shown what we want to show, and that's the end of that part. Part 3. The particle takes 3 seconds to reach the ground. By finding a formula for x as a function of v, or otherwise, find h, the height of the ground. So the piece of information that we're given in this part of the question is that it takes the particle 3 seconds to reach the ground. So when it hits the ground, t is equal to 3. Its displacement x is going to be h because that's the distance from the starting point down to where it is now. So its displacement is h. The velocity, we don't really know what the velocity is at this point. Okay, so the velocity is unknown at this point in time. Now, what else did the question say? It's suggested to find x as a function of v. It does say or otherwise, but the question's saying find a formula for x as a function of v. So if you don't have any other idea about how to go about this, that's probably a good place to start. So here we've got that differential equation from part I, except we made a common denominator and substituted in g as 9.8. But we've already seen this in part 2. So we want to find x as a function of v, which means we want to rewrite acceleration as something involving v's and x's. And we know that acceleration can be written as v dv dx, and that's good because it involves v's and x's. So this is going to be equal to our right-hand side, 4,900 v squared over 500. If we rearrange this, and we bring this to the denominator here, and then bring our dx up to the numerator here, so we're sort of cross-multiplying in a way, we get v dv over 4,900 minus v squared equals dx over 500, and then we want to integrate both sides here. All right, now this integral is very easy to integrate. We're just integrating a constant. This will turn out to be x on 500. This integral here looks a little bit messier, but actually it's not that bad. All we need to do is multiply top and bottom by -2 rather. And this turns into a log because the derivative of what we have in the denominator is minus 2v, which is what we now have in the numerator after multiplying by that constant. So this just turns into a log, minus a half log of the denominator minus v squared. And now it doesn't really matter what side we put our constant of integration on. I'm just going to put it on the right-hand side, and we can call it c hat. We don't want to call it c because we already had a constant of integration in part 2 called c. So I'm just going to call it c with a little hat on top of it. All right, but now we need to work out what this c hat is. So we have to look at some condition that we have in our problem. And that's where we're going to use, let's see, we're probably going to use this bit of information here. Now at this point, we know that t is equal to 0, but we don't have any t's here. We're dealing with v's and x's. We know that v is equal to 0, and we know what x is. X is the displacement, and at the start, there hasn't been any displacement at all. It hasn't moved, so its displacement is x equal to 0. So we can use that bit of information now. We can say when x is equal to 0, the velocity is equal to 0, and we can substitute that in. And we get minus a half log of 4,900 is equal to 0 over 500, which is just 0, plus c hat. So this is c hat. Now let's substitute that value of c hat back into this expression here. So we don't have that c hat appearing anymore. We have minus a half log 4,900 minus v squared equals x on 500 minus a half log of 4,900. And since we want to get x in terms of v, that means we want to make x the subject, we're going to move this constant term over here and it will become positive. So I have a half log of 4,900 minus a half log 4,900 minus v squared. That's equal to x on 500. Now we can combine these two logs together using our log laws. We get a half log 4,900 over 4,900 minus v squared. That's equal to x times 500, x divided by 500, but I want to get rid of that 500, so I'm going to multiply both sides by 500. When I do that, we'll get a 250 sitting out here, because a half times 500 is 250. Okay, so now we've got x in terms of v, but how does that help us? Remember, what are we trying to do? We're trying to find the height. We're trying to work out what h is. Now, this is an expression for x in terms of v. If I had the velocity at this point, I could substitute in x equal to h and v equal to whatever the velocity was, and I'd be good. I'd work out what h is. That would be perfect. But we don't know what the velocity is at this point. Is there a way we can work it out? Yes, there is. If we go back up to part 2, we found an expression for velocity in terms of t, the time. But we know what the time is at this point down here. The time is 3 seconds. Yeah, 3 seconds, I believe it's seconds. So if we substitute t equal to 3 in here, we would work out what our velocity is, which gives us that value there. Then we can substitute that value back down into this expression here for v. So that's our plan of attack. So when t is equal to 3. What's the velocity? Well, the velocity is going to be 70 times e to the 0.28 times 3 minus 1 over e to the 0.28 times 3 plus 1. And when you put that into your calculator, you'll get 27.78513, etc. And I would recommend that at this point, you don't clear your calculator. You leave that answer stored in the memory of the calculator, stored as answer, ANS. But this is good. We've got this bit of information. Let's go back to our diagram and add that in. It's no longer a question mark now. We know what the value of V is. The V at the ground, when it hits the ground, is 27.785 ... Okay, now the reason I'm saying ... and not rounding off is because we're going to substitute that value in to this expression up here. And you can see that I'm substituting inside of a logarithm. And logs and exponentials, you really need your most accurate answer when you're substituting into those, because even a small change in the number in here can result in quite a large change overall. So that's why I'm saying store it as answer and just press answer squared when you're typing this into your calculator. So at this point now, we can say at time t equals 3, the x value, the displacement is h units, or h meters, and the velocity is 27.78513 ... Okay, so we substitute those values into this up here. So I'm going to write it sort of back to front. X is equal to h, so h equals 250 log of 4900 over 4900 minus this value here, 27.785 ... and we want to square that. Okay, so but in your calculator, what you'd be typing is just answer, ANS. You press the ANS button and then you square it. When you do that, you should get your final answer, which is 42.86 meters, rounding off to 2 decimal places. Okay, and that's the final answer and the end of question 13.